All right, guys, this is the second part of 9.1 simplifying radical expressions. And we're going to talk about rationalizing the denominator, the hardest part of this section. Okay, rationalizing the denominator. As I always say in class, try to think about what these words mean. And what we want is we want the denominator to be a rational number. I don't know if you guys remember this, but if you take for instance, the square root of a non-perfect square, like square root of 3, it is an irrational number, which means that it's a decimal that goes on forever, doesn't repeat, so it doesn't terminate, doesn't repeat, and therefore is irrational. It can't be written as a fraction because it doesn't terminate, so it doesn't have that last decimal place to identify what the denominator would be as a fraction. I know I'm saying this fast. You can slow it down. You can listen to it a million times. But the idea is we can't have a square root or a cube root in the denominator of a fraction. So when a radical is in the denominator of the fraction, you can multiply the fraction by an appropriate form of 1 to eliminate the radical from the denominator. What does that mean? This is not an equation. We can't use any of the properties of equality or anything like that. The only tool at our disposal to get rid of this radical in the denominator is to multiply this by 1. We need to multiply by some fraction where whatever's in the numerator is also in the denominator. Okay, this process is called rationalizing the denominator. How are we going to do this? Well, you probably remember something like this. If you have the square root of 4, man, this thing's so hard to use. That's equal to 2, correct? Okay, so then what is the square root of 4 times the square root of 4? Sorry about this again. The technology is amazing. Well, this is evaluated as 2. This is evaluated as 2. So isn't that equal to 4? So in other words, the square root of 4 squared is equal to 4. So by squaring a square root, you end up with whatever is in the radicand, whatever's inside this radical. Okay, why does that matter? Well, if we now look at our amazing property, let me erase this. If we use our product property of square roots, do you remember how the square root of a times b can be written as the square root of a times the square root of b? Well, what if we went backwards? What if we started with the square root of a times the square root of b, and we went backwards back to here? What do I mean by that? Well, what if, and you may not know why I'm doing this yet, but what if we multiplied by the square root of 3n over the square root of 3n? Well, look at this denominator. Square root of 3n times the square root of 3n. That's like the square root of a times the square root of b, right? Well, what's going to happen is we're going to get the square root of 3n times 3n, right? Well, what's that? That is the square root of 3n times 3n is the same as having 2 factors of 3n. So we're taking the square root of a perfect square. What's that equal to? We'll just focus on the denominator for now. What's that equal to? Well, it's just 3n. Which is brilliant because what was our whole goal? To get rid of the radical in the denominator so it's a rational number. Perfect. Well, now we have to take care of up here. Well, we have the square root of 5 times the square root of 3n. That's the same as the square root of 5 times 3n, right? We're doing this product property of square roots backwards, right? We're going back from here to here. Okay, that ends up just being the square root of 15n. Sweet. We've gotten rid of the radical in the denominator. We've rationalized the denominator. Okay, what about this one? Here's the issue. We're still going to do the trick where we're multiplying by 1, but we have a cube root. How does that change things? Well, remember that the product property of square roots can be extended to cube roots, right? So I can make that 3 a cube root. I can make that a cube root. I can make this a cube root. Well, now think about what's happening here. We have the cube root of a. We want to multiply by the cube root of something, a cube root of b. And what's going to happen is a is going to multiply b, right? 9 is going to multiply some other number b that we haven't decided on what it is yet. Well, what do we want to have happen? We want the product of this thing to be a perfect cube. Why do we want it to be a perfect cube? Well, we can take the cube root of a perfect cube. Now, in the last video, I went over some of the perfect cubes. Here they are. 0 cubed is 0. That's not going to help us. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. And so on and so forth. Well, 9 times what is one of these numbers? Hopefully you see 9 times 3 would be 27. So if I make this the cube root of 3, and of course I'm going to want to multiply by 1, right? I'm multiplying by 1 here, so I'm not actually changing the value of the expression. I have the cube root of 9 times the cube root of 3. It's the cube root of a times the cube root of b is equal to the cube root of a times b. 9 times 3, that's the cube root of 27. Okay, why is that so rad? Because the cube root of 27 is just 3. Oh, we've rationalized the denominator again, right? We've gotten rid of that radical. All we have to do is take care of what's going on up here. Well, that 2 is going to multiply the cube root of 3, and I don't think there's anything I can do there, so I'm just going to leave that as 2 cube root of 3, and we're done. That's rationalizing the denominator in that case, but what about this case? See, here where we started, we only had a radical in the denominator, right? One term. Here, terms are separated by addition and subtraction. We have 2 terms. That's going to mess everything up. Now, I could read through all of this, but I'm not going to, just to save myself time. Let's think about what's actually happening here. First, if I tried to, and you don't have to write this down, this is just me showing you. If I try to do what we did last time, okay? If I try to do what we did this last time, I'm just looking at the denominator here, so I'll just put denom, just the denom. I'm not looking at the numerator, just the denominator. If I try to do what I did last time, where I multiply this by, let's say, root 3, okay, trying to get rid of this, so I get the square root of 9. The problem is that this is a factor with 2 terms. This factor is going to multiply both of those terms. So I'm going to get 2 root 3, right? The root 3 is going to distribute to the 2. My pen stopped working. Minus, the root 3 is going to distribute here. Well, that's cool because this is square root of a times the square root of b up here. Imagine the cubes weren't here. Square root of a times the square root of b. You get the square root of a times b. That would be minus the square root of 9, right? Well, that turns into 3. Sweet, but if we do this, and remember we're working in the denominator here, do we still have a square root? Yes. Oops. So what we're going to do is we're going to reach back, way back to when, into the last chapter. I've selected my eraser, but it's not working. Oh, there we go. Okay, we're going to reach way back into our last chapter, and we're going to see a trick that we can use here. Okay, I'm going to actually do this problem. We want to get rid of this radical in the denominator because we want to rationalize the denominator. Okay, I'm going to write in parentheses 2 minus root 3. Okay, now under here, I'm going to show you some algebra that's going on. Would you agree that this is a minus b? Right? Isn't that a minus b? Well, I know I can multiply a fraction by 1 and not change its value, right? I want to get rid of that square root. Well, reaching back into the last chapter, we did something where we multiplied binomials in the form a minus b times the quantity a plus b. And what did that result in? If you FOIL that out, you're going to get a squared minus b squared. Why is that awesome? Because you're going to end up squaring 2, and more importantly, squaring the square root of 3. Now when you square square root, you end up with what's in the radicand, this 3 that's inside that radical. So what we're multiplying by here is not 2 minus root 3, but 2 plus root 3. And of course, if I multiply by that in the denominator, I have to also multiply by that in the numerator, right? Because we want to multiply by 1, so we don't change the value of this fraction. Now, what's going to happen here? You're going to end up with a minus b times the quantity a plus b. it's going to be a squared, 4 because it's 2 squared, minus, what's the square root of 3 squared? It's just 3. So squaring a square root, you end up with just the number. Now that 7 is a factor that needs to multiply to both terms in the second factor. That's 14 plus 7 root 3. In other words, we have 14 plus 7 root 3 over 1, which you don't even have to put the over 1, of course, but doing it doesn't change anything. Notice what we've accomplished. We've gotten rid of the radical in the denominator. Careful on big ideas, they'll probably just want 14 plus the 7 square root of 3, and this thing's working so awesome. But the fact is, we wanted to rationalize the denominator by getting rid of the square root. But when there was 2 terms, we had to use our special product pattern, a minus b times quantity a plus b. Okay, when you have a form like this, a minus b, we call the conjugate. When you say, instead of 2 minus root 3, it's 2 plus root 3. This is the conjugate. 2 plus root 3 is the conjugate of 2 minus root 3. And the reason that a conjugate is important in this case is because of this special product pattern, which allows us to get rid of this square root. So the conjugate is just a fancy name for, hey, whenever you hear conjugate, it means that we're looking to use this special product pattern to get rid of a square root when there is more than one term in the denominator. Okay, as always, I'm going to post this on Google Classroom, and please ask any questions on there. Of course, the homework questions are going to be way harder than this, as math teachers always do, but I'm going to do my best to help you out. Thanks, guys.